this last conference is dedicated to concept tools. At the how we can approach the geometry and the geometry of the brain. We have a lot of conferences. All of them use it directly or indirectly, but none of them was expert in geometry, saying, here are the tools, here is the way that we use it, etc., etc. So I was thinking, we had a program, and I defined the program kind of knowledge should be given to the audience. What are the tools? What kind of mathematics are behind this? And this is really, really helpful when you think about your own problem. You know that, oh, this theory exists. Of course, you're not expert. This theory is hard. But you can get it and you can know. And this is also my focus this morning. So I am pleased that Elkaioum Moutuou accepted to this chart. It's showing us the way that we have to look to the geometry. So just to introduce Elka, Elka did his master at École Polytechnique in France. We call this school LIX. This is, from my point of view, but this is the point of view of all people who knows what this school is. This is the top there. And he did it in mathematics. Then he joined a very famous group at l'Université Lorraine, where he did his PhD in algebraic topology, so geometry, meaning that his brain is completely so where he developed a very fundamental concept. When we meet, I see those concepts. Oh my God, this is exactly what I am thinking about, but I have never go in this area. So I just catch him, bring him to Concordia. He is a researcher at Concordia in my team, and he is really developing this area, this direction of research, how we can use the groupoid and in geometry. And what does it mean when we talk about structures and function of the brain? Because we can talk about it regarding the neurobiology, biology, neuroimaging, but never with mathematics. So that's exactly what it is going to give us, like a first introduction to this homology and geometry. And this is his lecture. And the second part is how we can use this to study the structure of the brain, and more than just simply structure of the function. So he is going to explain this part of it. So thank you very much for your support also to the school, because he was here every morning supporting the school. So that's a very important aspect in my point of view. So thanks.
Okay. So thanks very much, Habib, for the great introduction, and also for giving me the opportunity to show you how algebraic topology can be used to study the brain. So indeed, when I met Habib, so he talked to me about his desire to develop some fundamental formalism in order to model structure and function in a more rigorous way. So at that time, I must admit that I was quite ignorant in many things in neuroscience. So I'm now still transitioning from pure math to more practical science, which, as Andrea told yesterday, also amounts of to changing somehow the mindset. coming from an environment where I used to think more abstractly. So now I have to look at things how they are, because usually, I mean, in the real world, things are not as beautiful as we mathematicians would like them to be. So, so over the last 2 weeks, you've heard a lot about complex networks, so graph theory, be it in modeling functional connectivity or structural connectivity or whatever. Or you've also heard about multilayer networks. So today I'm going to give you the basics concepts to know about graph theory, and even more, we'll show you that actually graph theory is not really sufficient to model all we want to understand from connectivity. And therefore, I will talk about simplicial complex and try my best to convince you that this is the actual basic tools we really need in connectomics. So I will start by an example from social sciences. So there is some the title of my talk is actually Homology, simplicial homology. And the Hodge-Laplacian. Okay, so here is an example. I will talk about social contagion. So you might have heard of this idea of social contagion, which actually concerns about how, for example, how rumors spreads over society, how opinion, how fake news spreads, how we adopt some social norms in our society. So here is the question: how do we model social contagion? So far, most people have been using graph theory to model this, meaning that, okay, so I have a friend of mine who shares some opinion. So this is my friend. I'm here. I'm connected to him or her. I adopt the same opinion or the same mode. So this is a graph. But of course, I think you will agree with me that this is overly simplistic. In reality, just because my friend shares some opinion doesn't mean that I will share the same opinion, right? So in fact, what happens is that there's some threshold in terms of the number of people you know, after which, I mean, you might share the same opinion as them. I mean, if you have, suppose you are here, you have other friends, so you belong to a fully connected group of people who shares the same opinion, then you are most likely to share the same opinion as them. Okay, so, and let's say this is the group of people you know that share the same norms or social norms, then you share the same social norm with them. Now, afterwards, if you know somebody, this guy knows that you belong to a huge group that share the same social norms, then they are most likely to share the same norms or same opinion, and they will spread the same thing to their social group. Okay, so of course, if this guy also knows this guy, that will strengthen the opinion of this group and also of this group. So now a graph theorist, so now I have a space. This is some space, I mean, society, and have a huge cluster here and some cluster here and a void here. So I can ask you how to analyze this graph. So if you use the graph theory tool, you'll say, okay, I have a cluster, I have another cluster, it's anything here and nothing here. So this nothing will mean nothing for you. But actually, in this example, you can see that, in fact, this cycle, let's call it a cycle or a hole, because there is nothing here, actually means something. It means a lot. It is as much important as the clusters we see here. Why? Because if this cluster shares the same norm, so these two guys will spread the same thing, and then it will go to here, and the same information will come back to the same group, and it will strengthen as well. So in fact, the both group will feed each other. Okay, so they will say, okay, in fact, there's another group that share the same thing, and this group shares the same thing. So it must be true. This opinion must be true. Oh, I mean, of course, I'm simplifying things, of course, but just for you to understand that, in fact, this is called hole or cavity topology. So I will show you now how to encode these kind of structures. The fully connected structure, like this one, and the void or the holes in a space. So now I will call the whole thing a simplicial complex. If you want to make an analogy with the brain, this whole might be interpreted as something that allows parallel processing, for example. So the information comes from this cluster and comes from here, and it go back to the other cluster. Or maybe these two guys actually allow both clusters to achieve the same process at the same time, synchronously. So what is a simplicial complex? Here are the basic building blocks. So in a graph, you have nodes, and let's call them zero simplex. But you also have edges, so links, the links between two nodes. So edge, and let's call them one simplex. So one-dimensional simplex, zero-dimensional complex, one-dimensional complex. But you also have three nodes that are pairwise connected, a triangle. Now we'll call them a full triangle. So we'll differentiate between a triangle, a void triangle, and full triangle. I will give you the distinction. So this is a triangle, and of course these are two simplexes. And the fourth dimensional, yeah, okay, there is 1 degree shift, of course. So if you have 4 fully connected This is a tetrahedron. Or 3 simplex, etc., etc. So these are the basic building block of a simplicial complex. So what I mean by a full triangle, in fact, these objects in reality are intrinsic to the structure of the space. What I mean by that, so again, let's go back to the friendship, the social network. So there is a difference between a group of 3 people who are pairwise connected. For example, let's say, so I like the example of co-authorship. Co-authorship, it's a social network. So suppose 1, 2, 3. Suppose that 1 and 2 co-authored the same paper, 2 and 3 co-authored the same paper, and 3 and 1 co-authored the same paper. Here, the links are co-authorship. So that would give you 3 papers. The 3 guys didn't co-author the same paper. Okay, so this is not a 2 simplex. If you consider the social network formed by co-authorship, in that case, this is not a triangle. It's not a full triangle. It's a cycle. However, if you have 3 people who co-authored the same paper, then there is a link between 3 people. So that is a higher order interaction between 3 people. So you can see that, in fact, the idea, the very concept of simplicial complex gives you much freedom in defining what is an interaction, what is a link, than graph theory, meaning that you have higher order interactions. Okay, and that cannot be, this configuration cannot be modeled by graph theory, correct? And it's also the same thing if you want to, for example, in some case, you want to study the brain and you have some way to measure activation of brain regions. And you say, okay, so a triangle for me, or a link, means 2 regions that are active at the same time. So in that case, you would like to link 3 regions or 4 regions that are active at the same time, which is different from 3 regions that are pairwise active at the same time. You see what I mean? Yeah. So, yeah.
So this is the weight of whatever the connection between the edges, is that, or how is the weight of
Okay.
or similarity?
Okay. For now, I don't consider weight. It's a binary thing. So either there is a link or not. But of course, you can add weights as well. I mean, yeah, if you add weights, in that case, you might have weight for pairwise link and weight for 3-wise links, etc., etc. That would be different. So, and in that case, a link, the weight of a full triangle would not be the sum of the weight of the edges. That would be different.
So when this code between them is filled because the 3 are, so does it not become just 1 node?
No. Yeah. Okay. That's a good question. So you see that in fact in computing the homology, that would be considered as a node. Yes. Or 0 in homology. Yes, absolutely. And of course, you can generalize this for higher order interactions, etc., etc. So now, how do we? Your question actually anticipates the idea of homology. Okay, so I will start with this kind of thing. So I have one, let's say 1, 2, and 3. Let's say I have this very simple graph composed by just one edge and one node. You can see that, I mean, it's two pieces, two connected components. Okay, so this is G, two connected components. But how do we compute this? How do we, I mean, how do we prove rigorously that this is two connected components? Of course, you see, it is important to know because, I mean, if you have a more complex graph, you would like to know how to actually to compute the connected components. So this is a homological question, in fact. So I will consider these two vector spaces. So C0, the vector space that is generated by the nodes. So 1, 2, 3. Let's call this edge A. And the other vector space is generated by just the edge. We have only one edge. Okay, let's make it a bit, yeah, that's it. So A. So I recall just that for vector space, E means that you have some operations. You can add elements of E, and these are some concepts I will be using. And if F is a sub-vector space of E, the quotient E over F means that, in fact, this is generated by just F of F with the idea that the quotient here means that every element in F is considered as 0. That's it. You just erase F in E. You annihilate it in E. That's the quotient. Okay, so I have C1 and C0, and I define this map from C1 to C0 by D of A is equal to, so what is A? A is the segment, this 1, 2. I say this is 2 minus 1. So I'll make like this just to distinguish between the numbers and the symbols they represent, because here these nodes represent only symbols. When I say C0 is generated by these elements, they are just symbols here. So I'm just concocting a space. I decide to add some operations on them. Okay, so this guy. So this is my function, and I define now H0 to be the zeroth homology group, to be just C0 over the image of D. What is the image of D? The image is formed by all the elements in C0 that are, of course, the image of D. That's it. Meaning that everything here but the image. So what is C0? What is H0? So H0 now, Okay, so I might use this one. So yeah, okay. So if you wanna take all the elements of C0 and consider everything inside here to be zero, that means that so C0 is 1, 2, 3, and you can see that in fact 1 is equal to 1 2 minus 1. So you might just 2 is equal to 1 minus actually 2 minus 1 plus 1, right? 2 is equal to 2 minus 1 plus 1. And I want to show that actually, oh no, this is not what I want to show. Okay, what I'm showing is that in fact, if you consider this space, you might, in this space, 1 is the same as 2, meaning that in fact, this segment becomes just 1. You are zooming out, in fact. In this space, you are zooming out your graph. So in that case, you will only see one piece and one piece, one node and one node. This is the intuition behind this homology thing. So how do you show that 1 is equal to 2 in this space? You just consider this thing that in fact everything, so this thing here 2 minus 1 is 0 in this case. That's it. Because in this space, in H0, 2 minus 1 is equal to 0. So 2 is equal 1, which means that, I must recall that elements in the quotient are called class. So the class of E in this thing is all the elements of E such that E minus this element belongs to F. That's it. So 2 is equal to 1 in this space. So they represent the same thing in H0. But of course, 3 is left alone. There's no way to write 3 as this difference. It's impossible in this case because it's completely separate. There's no, if there was a link between 3 and 1, in that case, 3 would be equal to 1 would be equal to 2. You would have only one piece. See what I mean? So this means that H0 is only generated by 2 elements, the class of 1 and the class of 3. Yes?
So if you have a link between 3 and 1, you say that 3 is equal to 1 and equal to 2.
Yes. Yes.
So does that mean that implicitly there is a link between 3 and 2?
Yes, yes, yes. Because, I mean, in fact, in this homology, the zeroth homology, all the links, they link, I mean, a node to, to the other node. So the 2 nodes become 1 point. So it only sees pieces. That's it. So everything, no matter how, so if you have 2 nodes that are connected by a long path, it doesn't matter.
So in this case, A, which is the edge, it exists. It's a spatial distance between, say, 2 generators who are creating the same behavior.
Yes.
But this distance is not, it's still there, but it's not 0. That's the idea.
Yes, 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 yes. So yeah, so this space will not see the difference. Yeah, no matter how the distance is. Yes. If you want to count the distance, then you need to go higher in higher dimension. Yeah. So this is so it's generated by two elements. So we say we define the Betti number. So the 0th Betti number is beta 0 is the dimension of H0. In this case, this is equal to 2. So the 0th Betti number is just the number of connected components of your graph. So you might have guessed that we can go higher. So now, instead of this very simple graph, let's consider a more complex one. Now we have 1, 2, 3, and so this is a full triangle. 1, 2, 3, 4, 5. And let's call this edge E1, E2, E3, E4, E5, and E6. So there is a 2 simplex and a hole. So the idea is now how do we compute this hole? Because that's the thing. So again, if you zoom out, because this is a full triangle, like you said, it will become 0. You will only see this void, this cavity. So the idea now is to compute this cavity. So now we do the same thing as for the other example, except that now C0 will be generated by 5 elements. So generated by 1, 2, 3, 4, 5. And now C1 is generated by 6 elements. E1, E6. Now C2 will be the space generated by the 2 simplices, the triangles. We have only one triangle. Let's call it well, let's not alpha. Okay, so alpha, which is just on parenthesis. So in fact, in order to compute this homology stuff, just for computational purposes, we need to decide on some orientation, orient our graph. So let's orient this way from lower order to high order in the numbering of the nodes. 1, 3, 3, 4, 4, 5, 1, 5. So it doesn't matter how you orient, but you just need to be consistent in the computation. So meaning that because we ordered this way, we will write E1 is equal to 1, 2, etc., etc. That's for computational purpose. So now 1, 3, let's order this way, orient the simplex this way. So alpha is 1, 2, 3. Generated by 1 element. Now we do the same thing, except that we have now 2 maps, C2 to C1 and C1 to C0. So the delta we used there, we will call it now delta 1, so D1. And this one, we'll call it D2. Now, D1 is the map from the edges to the nodes. And D2 is the map from the triangles to the edges. So we want to transfer. So these are called boundary maps, meaning that we are only taking the boundary of the simplices. So remember what we did here. In fact, this D, the only thing we did was just to dissect the edges and take only the boundary element. The boundary here is 2 and 1. So for triangles, the boundary will be the edges. They are also called faces, in fact. So D1 of E1 will be, now we take the last one minus the first one. So E1 is 1, 2, so 2 minus 1, D of E2, E2 is now 3 minus 2, and D1 of E3, 3 is 1, 3, so 3 minus 1, etc., etc. Now, what is D2? There's only one element in the two-dimensional space, three-dimensional space, actually. So D2 of alpha is D2 of 1, 2, 3. So I will give you the general formula for this. So, but in fact, what we do, the way we define these maps, we first remove the first element in the simplex. So if we remove this, we get just this edge, 2, 3. So it's 2, 3. And then we put minus, and we remove the second element, and we take only this one, 1, 3. And then plus, now we remove the last one, 1, 2. This is now our D2. So we can show that, in fact, D1, when we apply D1 to D2, meaning that after we have applied D2 to this triangle, when we apply D1, this will be 0. Yeah, easy to show that. We just apply, so because this will be equal to D1 of the whole thing of this 2, 3 minus 1, 3 plus 1, 2. And now when you apply these formulas, they all cancel themselves. It's 0. So what does this mean? This means that, in fact, the image of D2 is in the null space of D1. This means that the image of D2 is a subspace of the null space of D1. It is called the kernel. So the kernel of a map is just all the elements that are 0 when applied onto by the map. So it's a subspace of this thing. So because it's a subspace, we can define the quotient again. So H1 now is just the quotient, so the kernel of D1 over the image of D2. This is now H1. In fact, this is the same idea, the same underlying idea we used in defining H0. We just took C0, but C0 could be seen as the kernel for the 0 map. So if you define delta 0 as just the 0 map from C0 to 0, then C0 will be definitely the kernel of this thing because everything is mapped to 0. Okay, so Now, how do we compute this space for our graph? It's just basic linear algebra that we need. Okay, let's compute H1 for the group, for the graph we have. Well, the simplicial complex. It's not a graph, it's a simplicial complex. Okay, we must first find the kernel. So what is the kernel of delta 2? So this is a vector space. So it's a sub-vector space in C1. Where yes, in C1. No, the kernel of delta 1. Yes. So H1 again. So H1 is the kernel of the D1 over the image of D2. Okay, so what is the kernel? So remember that the kernel is inside C1, and C1 is generated by all the edges, 6 edges, 6 elements, meaning that every element here, if we write omega in the kernel, we can write it as a linear combination of the generators of our space. That's the whole idea of a vector space generated by some element. So meaning that because omega is in C1, then omega can be written as x1 E1 plus x2 E2 plus x3 E3 plus x4 E4 plus x5 E5 plus x6 E6. We are just applying the very definition of a vector space generated by 6 elements. That's it. Okay, so now, because it is in the kernel, then delta 1 of omega is supposed to be 0. Which means that, so delta 1, so of all this stuff, so in fact, I will write this way, xi delta 1 of ei is 0 for I 1 to 6. So when you apply just this formula, what you get is a linear system. So you just need to solve a linear system with 6 unknowns. That's it. Okay, so yeah, if you want to have fun, we can do this together. Okay, let's go. So so what I have here is I will have x1, so d1 of e1. We know what is d1 of e1, 2 minus 3, 1, sorry. So we'll have x1, 2 minus 1, plus, okay, I think I need more space. So I will have x1, 2 minus 1 plus x2. What is d of e2? So 3 minus 2 plus x3. Sorry? 3 minus 1 plus x4. 4 minus 3 plus x5. 5 minus 4 plus x6.
So 1 minus 5 minus 1.
5 minus 1. Thanks. And this is supposed to be 0. So this means, so I will regroup everything. So first one. For one, I will have, so x1, I have 1 here as well, minus x3. I also have 1 here, minus x6, right? I think I didn't. Minus x1, thank you. Yes, plus, so for 2, I will have x1 minus x2. I have, that's it, right? So x2. So remember, the unknowns are at the x's, but all the numbers here represent symbols, just the generators of our space. So now for, I did for 1 and 2, now 3, I will have x2 plus x3 minus x4. Okay. And now for 4, x4 minus x5. That's 4. And for 5, I have x5 plus x6. And that's it. And this is 0. Yeah. Yes. Good. Yeah. So now I am in C0. Correct? I'm in C0. I have all the generators of C0. So what this equation means, because I have all the generators of C0, so remember, in linear algebra, when you take the generators of your vector space, a linear combination, this is a linear combination, is 0 only if all the coefficients are 0. So that means that everything here is 0. So I will have minus 1, x1 minus x3 minus x6 is 0. x1 minus x2 is 0. x2 plus x3 minus x4 is 0. x4 minus x5 is 0. x5 plus x6 is also 0. So now just some elementary stuff, and we solve this thing. And we'll get, so basically here, I'm not gonna finish this, but although why not? Do we have time to? No? Okay. So basically we should find a two-dimensional, so 2 vectors, 2 solutions here. So I will call it V1 and V2. So those are the vectors that generate the kernel. So the kernel of delta 1 is generated by 2 vectors. And now H1 being the kernel, so 2-dimensional space over the image, but the image of delta 2 is a 1-dimensional space. This is generated by just the image of the triangle. So that means it's generated by only this element, 1 element. That's it. So it's a 1-dimensional space. So I have a 2-dimensional space quotiented by 1-dimensional space. So I get just 1-dimensional space. So in fact, H1 will be generated by only the class of V1. So beta 1 is 1. So so beta 1 is the dimension of H1, the first Betty number. So the bit one is just the number of holes in your simplicial complex. We have only one hole added inside. It's computed by this thing. So I think you've got the idea of homology. Yeah. So the whole idea of homology is that you have a space X and n simplices. So what we do is to take Cn to be the vector space generated by the n simplex. Sometimes simplices as well. And you define Cn, Cn minus 1, etc., etc. So d1, dn, dn minus 1. So for each dimension, you have a homology group. And Hn is the kernel of dn over dn minus 1 over the image of dn. So the image of each map here is inside the kernel of the following map. That's the idea. So, and the formula is pretty simple. You just take all the boundaries and you play with the sign. Okay, so now in practice, how do we compute? Of course, you might guess that it's highly combinatorial, and you would not try to compute homology by hand for highly complex simplices, but there is a way to do that and to implement the computation quite easily, and it is by using a generalization of the graph Laplacian. You've also heard about this, the graph Laplacian, which is used mainly to study dynamics on networks. And diffusion, etc. So the idea of the Laplacian, we will start by with the graph Laplacian, is again pretty much the same as what we did for the spread of rumors, but now suppose that you have some resources on your nodes, or energy, or molecules, and it diffuses across the network. And you want to study how it diffuses across the network. So this is called diffusion processes. You are familiar with this idea. And for example, you have your graph, and for each node you have the resources at time t. So the model is given by this thing. So the rate of change of the xi are given by the sum of ij, xj minus, so in fact, so xj of t minus xi of t for j in the j connected to I. So this is how you model diffusion on a network. So, but this can be written as the sum of A, Ij, xj of t, where A is the adjacency matrix of a graph minus this is I'm going to play with the degree, so I will write this way. So no. This is nothing but the sum minus the sum of Lij xj of t, where Lij is the entries of the Laplacian matrix. So the Laplacian is defined as the degree minus A, where the degree is, so I will write this way, let's say di. The Laplacian of a graph is just the degree matrix, the diagonal matrix formed by the degree of your nodes minus the adjacency matrix. Okay, so this is D1, the N, and A is the adjacency matrix. So this is how you model diffusion process. So this now, if you take all the vectors, so x of t to be x1 of t, so you take all the states, all the resources of the nodes at time t. So this equation means d of x over dt is equal minus L of x of t. And in fact, what is the relationship between this equation and homology? It's simple. In fact, it is known that when you take the spectrum, the eigenvalues of the Laplacian, the graph Laplacian, meaning all the real numbers verifying this thing, so I'm sorry, such that when you apply L to a vector, some vector, you get lambda v eigenvalues, and you take the zero for lambda is equal to 0. So the multiplicity of these eigenvalues, the multiplicity of the 0 eigenvalues is equal to beta 0. So the multiplicity of the 0 eigenvalue of the graph Laplacian is exactly the number of connected components of your graph. Then you that's homological property, in fact. So that means that, in fact, this equation, so the kernel, that means also that the kernel of the graph Laplacian is exactly H0. So the kernel, so the solutions of this equation are exactly elements or classes in the zeroth homology group of the graph. That's what it means. And in other words, this equation actually encodes the whole topology of the graph. But in fact, this graph Laplacian also actually gives us more information that homology dismisses, because this is only the zero eigenvalue. But what about the non-zero eigenvalue? For the non-zero eigenvalue, that they are not seen by the homology, and we are interested in this thing. So it turns out that when you take the largest eigenvalue L, and you take the eigenvectors corresponding to this eigenvalue. That also gives you some centrality measures for your graph. And this is exactly the centrality measures that are used by some algorithms like PageRank, that are the source of Google search engine, and other measures also like the I think the eigen measure used for citations for bibliometrics, etc. So this is only this thing, and also the smallest non-zero eigenvalue also means something, so it gives you some insights about the connectivity of the graph. But it's still unknown, at least in practice, what the other eigenvalues mean in reality, but they mean something, and we've been working on this both for graph and for simplicial complexes and multilayer networks. And I will be talking about this in my research presentation. But of course, since this is just the graph Laplacian, meaning that it's an operator defined only on C0, only on the nodes. But what about the edges? The Laplacian on edges and the Laplacian on triangles. And that's exactly Hodge theory. So it's a generalization of this graph Laplacian on high-dimensional structures of your space. And it also turns out that all those Laplacians are connected to the homology. Yeah, so I think we have more minutes or? Okay. Okay. So you can actually see, in fact, there is the link between the Laplacian and homology can also be rigorously proven by this thing. So remember that I define the sequence. So dn minus 1. It turns out that all these Laplacian. So in fact, let's take C1, C0, 0. So D1 is 0. So in fact, this L comes from this sequence. It's so remember, those maps are just matrices because we are dealing with finite dimensional vector spaces. So they can all be expressed by some matrices. So this guy can be defined by this thing as follows. So it's don't want to do a mistake. So you have C1, ID1. So those are vector spaces, meaning that you can endow them with some inner products. For example, just take the product, the usual product. So all those maps also have their dual maps, meaning that you have something like this. They're matrix. You just take the adjoint matrix. That's it. So, and then you go back again. So you can write this way. So this is equal to, so D1, D1T. Okay. So it's reasonable. So it's logical to say that, in fact, this graph Laplacian is exactly homological construction. And you can do the same for the other homology group. So now the kernel of L is exactly H0. So this is now a map from C0 to C0 because dt goes from C0 to C1 and D1 goes from C1 to C0. So you go from C0 to C1. Now you define L1, Ln from Cn to Cn in the same using the same reasoning, just by taking the operator and their dual and add something. That's it. Okay. Oh. Yeah. Yeah.
Just what you said. So I guess if we take the multiplicity of the zero eigenvalue of this L1, we get a beta 1.
Yes. Yes, exactly. Yes. Yeah. 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 The same property is valid for all dimensions. But of course, if you go to higher dimensions, so the beta 1 is corresponds to holes, one-dimensional holes, which means cycle. Now, if you go to 2 dimensions, so beta 2 will be also holes, but in 2 dimensions. For example, if you have think about a hole, I mean, an empty sphere, the hole inside would be seen by H2. If you get a torus as well, you have a hole inside, and you get. So this is just the combinatorial side, but in fact, yeah. For example, if you have a torus. So this, I mean, in fact, topologically speaking, this can be seen as just a cycle, 2 cycle, 2 circle. So 2 cycle, in fact, 2 circles and 2 cycles. So this thing is generated by, so think about a donut. So you have one cycle and 2 cycles, meaning that the only way to cut your donut, an empty donut, in 2 pieces will be to cut this way, because if you cut this way, what you get is a cylinder, right? Now, if you cut the other way, you get a flat space. So meaning that, in fact, the maximum cycles you can draw with, you can cut your torus without dissecting it, would be to do that. I mean, 1 cycle and 1 cycle, you get a flat space. Okay, so this is this cycle and this cycle. So the beta 0 of a torus would be, of course, what is the beta 0 here? You just have 1 piece. One piece, 1 connected components. And the beta 1, the cycles, so we'll have this cycle and this cycle too. Now, beta 2 is the void inside the torus. You have a void. So this will be 1. So 1 cavity inside. Yeah. So it's like a tetrahedron, an unfilled tetrahedron. But it's quite difficult to imagine void in 3 dimensions or 4 dimensions, but you get the idea. Yeah.
I can add this a little bit. So this is the general view of what the homology is. And at the end, the homology is the way that we look at holes within the topological space. We are quantifying this BT coefficient, and all the BT coefficients are related to holes.
Yes.
Okay, so this holes is an important feature within the geometry. You make a link between point of view of the homology, and you derive the Laplacian operator. So, meaning the first thing is that Laplacian operator gives information about space. But this is something maybe you know, that Laplacian is something who is related to the topology of the space. So this is important to have in mind. And it seems like with this formula, the Laplacian operator gives you, now move to the Laplacian itself. You mentioned this eigenvectors of the Laplacian, and you give this result as the first eigenvectors, but the eigenvalue corresponding to 0. The multiplicity of this eigenvalue corresponds to the dimension, and corresponds to beta 0. And beta 0 gives you the number of holes. So, and the number of holes, you interpret this like the number of clusters, the number of connected components.
Yes. In the 0th dimension, the holes are just the number of or the number of connected components. But the 0th dimensional holes.
So we can move to this number of connected components if I take a graph and I cluster the graph. So clustering the graph, looking at all the different clusters, I see that this graph can be well estimated by 3 component clustering. So the point of view of the clustering doesn't inform about the holes. It's informed about the clusters of organization. Okay, but this organization homology told me that this is the big coefficient. And so again, clustering technique with spectral method like Laplacian and homology give the same kind of result. So that's another point of view, who is very important. Now my question, you mentioned a little bit this. Okay, and what about the other eigenvectors? Because the homology doesn't say anything about this.
Yes.
First, why? Because we make a link between 2, and I think that the mathematician says, because I have this relationship, strong relationship between the Laplacian and homology. Why I don't have other features from the homology point of view who can inform about the other subspace that the Laplacian is going to touch? This is my question.
Yeah.
Is there any response?
No. Homology. No, because the reason is because the homology by itself is about dismissing some features and looking at just some. For example, the idea of considering a triangle as one thing, but one piece, no matter how the triangle is. So it doesn't say a lot about the weakness of the triangle, because you can have a weak triangle, for example. It doesn't differentiate between a triangle and another triangle. 2 triangles are the same anyway. So that's the whole idea of topology. Topology, for example, doesn't differentiate between actually a donut and a cup of tea, for example. They are the same topologically. But if you want to in reality, they are different. We know that they are different, and it doesn't, in that case, topology doesn't help at all. Then the spectral theory would help, differentiating them. So yeah. So I think the nature of topology itself doesn't really allow such a, you would need to invent some maybe some spectral topology, this kind of idea. Yes.
We need to invent, because yeah, we see that even if it seems like complex, it's very simple, because what this operator means in delta, we are simply, when you look at the object, you are looking at the frontier of the object. So we're not, so yeah, it gives some information when I look at the triangle, and I'm simply looking at the edges of the triangle. This is what our eyes do. This defines the triangle, but triangle can be defined maybe in a more complex way than just looking at this sample vision.
Yeah.
So in this case, the operator.
Yes. You can. Yes.
To give some information.
Yes, you can twist the definitions and of your simplices, because yeah, the freedom is in the definition of the simplices. How you define simplices. I mean, you are really free to define what a simplex is. And in that case, yes, although some idea like persistent homology could be in the same, could probably address what you're saying. So the idea of persistent homology is, in fact, so it's an idea that has been used to develop what is now called an established field called topological data analysis. So it's sort of the topological machine learning. So the idea is that you have some data set. You don't do any a priori, you don't do any assumptions at all, but you explore your data set in order to get some insights. So it's an exploratory data analysis techniques. So, and the idea is that when you have some data cloud, you have data points and measurements. So let's say an n-dimensional data. What you do is to define some notion of distance, either through correlation or entropy or whatever. So now it can be, for example, some data from DTI, for example. And what you do, so you have some number of fiber tracts between regions, for example, and you have a fully connected matrix. So now what you do is, okay, I will start by considering the empty graph. There's nothing at all. So which amounts of putting a very small threshold, very small threshold, in such a way that no connections between your points. And now you increase the threshold. Okay, so now you start having some connection. Okay, and then you increase again. Okay, not only now, so when I say increase, I mean you just link the points that are in the distance smaller than your threshold. Let's say you start by epsilon epsilon 0, and then epsilon 1, etc., etc. Okay, so now because you have increased, you start having not only connections but also triangles. And again, you have some circle will bond Okay, some circle will get birth and then they will die. So, okay, so you have, for example, this cycle, and after some point, this circle will disappear. You will have some connections, etc., etc. So what you see, so at each step, you compute the homology of the complex you get. Okay, but because you're changing the threshold, some simplices will be born, and at some point they will die. Some cycle will be born, and at some point they will die. So you will look at the structures that persist more than others. And at some point you will say, okay, it's fair to say that those who persist a lot are actual structures that are intrinsic of the data, and they give me some insights, real insights about my data, while others that were born at some point and they died and they never come back, they are just noise. Okay, so that's the idea of persistence homology. It's nothing new. It's exactly based on the simplicial homology I've talked about. It's just that you put some threshold in order to define your simplicial complexes at every step. So you have many simplicial complex, and you look at the structures that persist through this process. Okay, so it's a way of using this. It's quite spectral as well. I did something here, but I don't know.
One way, it does not cover.
No,
What I am.
no, no.
This notion of persistent is interesting. Because when you know that when you address the question of functional intelligence, you can correlate between area and degree. And depending on what we want to do, let's say covariance matrices, and we extract from the covariance matrix clusters, or we decompose this covariance matrix and we got components, and we identify those components like, oh, this is a cluster, and the cluster becomes like networks. And we say, oh, this is on the connectivity. I can extract the default model. I can extract the visual model. So on. Okay. So we can the data set as all the area of the brain, like the nodes, and the name is simply the covariance matrix, so the correlation between nodes. I can calculate the correlation between all the nodes. So I have a full graph. And from this correlation, depending on the statistics, let's say statistics told me all this correlation is significant at some level. So that took the level of the statistics. Should we take 1%, 2%, 3%, 5%, 10%? But we don't know. We usually will use alpha or 5% because this is what the statistics tell us. But sometimes, as we know, you have to adapt this. So let's talk from 1% to 10% because this is the physiology. I don't know. If you can go with 1%, you know that you are able to kill a lot of connectivity. So the graph becomes empty graph. 2%, 3%, 5%, 6%, 10%. And if you increase, you are going to have 1 graph. So following what that dimension is, okay, with 1%, I am going to see if there is a whole loop or not. So I can calculate the beta coefficient. Okay, and those beta coefficients inform about the holes that I have within the structures. Okay, let you do it with 2%. 3%, 5%. So if now I segregate enough between, don't forget, the whole is related to this lambda equal to 0 for the Laplacian operator. And lambda equals 0 for the Laplacian operator correspond to the component that I can extract from the graph. Component of the graph means networks. Okay, so I can see which network is now persistent if I am changing the threshold. And the one who are persistent, I may be there, and others are going to appear, disappear, and maybe this is simply the noise that I have from the data, and not the underlying structures of the general offshore. This is what we did. I think a year before when I was in France. So this, I introduced this theory in my team and we tried it. And I see that what we extract, not new, we extract things that we did with IPA method, but we extract those clusters corresponding to the motor, visual, default mode, and so on. All those networks becomes persistent. And at some times, nothing. But we can discover this from this connectivity, functional connectivity, simply looking at the geometry of the connectivity that we observe. Okay? And this comes with hope. This is one way to look at this geometry. So what about adding now the anatomical connectivity? What does it mean? How it was merged together? I think that this is your thought is the second part of it. Okay, so let's stop here.